Hi all, welcome to the first lecture in your fourth week. We are going to talk about third postulate, which concerns measurements in quantum computing. We have seen first and fourth postulate, which describes the state space or the state of the system. After that, we also looked at the second postulate, whose primary objective was to define operations on the quantum system. Obviously, the next question is going to be how to get the output. We know how the states look like, we know how we can operate on them, but how can we get the output of the system? This is what the third postulate exactly describes. You have seen some kind of action of the third postulate before. You remember, if our state is alpha 0 plus beta 1, we say that if we measure it in the standard basis, these terms will be exactly clear to you after this week. But we say that if the state is measured in the standard basis, then we are in state 0 with probability alpha square, and we are in probability in state 1 with probability beta square. This was an example of a measurement. Given the state, we can see what we will see as an output. Our target is to formalize this and say what exactly can be measured in a quantum system. As before, to do that, we need a bit of linear algebra. So we are going to learn about positive semi-definite matrices first. If you haven't seen them before, make sure that you pay close attention to them. These matrices are going to be important in our discussion of quantum computing. If you remember other classes of matrices, the important one was called the normal matrix, for which we had the spectral decomposition. These normal matrices were divided into two, not kind of divided into two, but we saw two different subclasses which were important. There can be matrices which are both Hermitian and unitary, but these were the two important subclasses. In the case of Hermitian matrices, we saw these matrices were the ones such that M was equal to M star, or other way to say it was that all eigenvalues were real. A natural restriction of these eigenvalues would be when all eigenvalues are positive. What happens if we apply this stronger restriction? What class of matrices do we get? As Indians, we love the number 0, so let's include that in our class. Let's say we want to talk about matrices such that all eigenvalues are non-negative. These matrices are exactly the matrices which are known as positive semi-definite matrices. This is one of the simplest characterization of positive semi-definite matrices. So, a matrix is PSD, which is short of positive semi-definite. The definition would be that a matrix is called PSD if and only if it is Hermitian. Otherwise, we can't talk about eigenvalues being real. We can't talk about eigenvalues being positive. They're complex numbers. We have no way of knowing whether they are positive or negative. First condition, it has to be Hermitian, and second condition, all eigenvalues are non-negative. Also, if all eigenvalues are positive, when we have a slightly stronger restriction, then the matrix is called positive definite. though mostly we will be concerned with PST matrices. They form a closed cone. If you don't know what it means, don't worry about it. Just it's important to know that this is the matrices which will feature again and again in quantum computing. Though sometimes if we make a slightly stronger restriction and we don't allow eigenvalues to be zero, then the matrix is called positive definite. Otherwise, when all eigenvalues are non-negative, then it is called a positive semi-definite matrix. In rest of the video today, we will see multiple characterizations of the same subclass, in the sense that we will see many other definitions if you wish. The two other definitions are going to be, first, a positive semi-definite matrix is something such that VMV is greater than equal to 0 for all vectors V in the vector space. You could have assumed that M is a square matrix. It is a linear operator over some vector space V. Then it is called positive semi-definite if for all V element of V it can be written as its quadratic form is greater than equal to 0. This is also called the quadratic form of M. So the quadratic form of M is greater than equal to 0, then the matrix is positive semi-definite. Other definition is that if there exists a B such that B star B is equal to our matrix M, then it's a positive matrix. One way to remember this would be to say that M has a square root. I am not making it rigorous at this point, but by the end of the video lecture, it will be clear to you. At this point, just remember, if you want to think of this characterization, you can remember the shorthand as that M has a square root. And this is what it means, that M has a. So it turns out that all the three definitions are equal. Remember the zeroth definition, M is Hermitian and all eigenvalues are non-negative. So we want to prove that all these three definitions amount to the same thing. Let's start by proving that 0 and 1 are the same. Let's look at this direction. That means we want to show that if condition 0 is satisfied, then condition 1 is also satisfied. In other words, if M is Hermitian and eigenvalues are non-negative, I'm sorry, I should just clarify this, all eigenvalues are non-negative, implies this quadratic form is positive. And again, our method of proof is going to hinge on spectral decomposition. As soon as we know that M is Hermitian, it has a spectral decomposition. Let's say this is the spectral decomposition. What do we know here? Lambda is are real and VI's form an orthonormal basis. Though we know that actually eigenvalues are not just real, they are positive. I mean non-negative. So I can just say all lambda is are greater than equal to 0. We know this. We know that M can be written like this, where lambda is are positive and Vi is form an orthonormal basis. What will V look like? Since Vi is form an orthonormal basis, that means I can write V as a linear combination of Vi's. So let's say it is alpha EVI. Our M was already written in this basis. Now let us calculate VMV. If we do this, you will notice that MV will turn out to be summation lambda I VI VI. This just follows from the fact that VI Vj is 0 or Vi is from an orthonormal basis. Now from this, calculate VMV. This is going to be summation I lambda I alpha I square. I'm missing alpha I here. So we exactly know what VMV is. These alpha I squares are greater than 0. I know lambda is greater than 0, implies VMV is also positive. So one direction is proven. Now we will prove the other direction, which is that if VMV is greater than 0, implies M is Hermitian and M has non-negative eigenvalues. The first part is actually easy. The way to prove it would be to show that if M is not Hermitian, then you can find a V such that this quantity is not even going to be a real number. So it cannot be positive. I will leave that proof to you, but that is something which you can construct. So if M is not Hermitian, then this condition cannot be true for all V. This you can show. Now our job is to show that all the eigenvalues are non-negative. That is not very difficult. Suppose lambda is an eigenvalue. That means MV is equal to lambda V. If this is the case, consider the quadratic form. VMV is VMV. This is V lambda V, the VV. Now by the condition, I know that this thing is greater than equal to 0. That means this thing is greater than equal to 0. Now this is obviously positive, implying lambda is greater than 0. So all eigenvalues are also positive. This shows that two conditions, 0 and condition 1, are exactly equivalent. We can either say that M is Hermitian and all its eigenvalues are positive, or we can just say that its quadratic form is positive. Now let's worry about showing that condition 2 is equivalent to 0, 1. We know that 0 and 1 are both equal. I will just remind you condition 2. Condition 2 says that M has a square root, and you want to prove that that is same as the positive semi-definiteness condition. This is same, M has a square root. Great. So let me prove that 2 implies 1. That is going to be very, very easy. If M is B star B, we are going to look at the quadratic form and show that it is going to be positive. We want to look at this. I am replacing M by B star B. I know they are equal, and then this requires something which we have known from a long time. I can move this B star here and remove the star. This is a simple property of Dirac notation. You can do it by converting it to a standard notation. I think you should know it by now. So once you move it here, this quantity becomes this, and since this is the net product between the identical vectors, this has to be positive. So this shows that if M can be written as B star B, then quadratic form is positive and M is positive semi-definite. This direction also turns out to be easy. Now only thing which remains to show is that if M is PSD, that means all the eigenvalues are positive, quadratic form is positive, we know all those are equivalent. If that is the case, that should imply that there exists a square root, which means a B such that B star B equal to M. How should we construct this square root? And again, our friend is going to be the spectral decomposition. I know M is PSD. M can be written as summation lambda I Vi Vi. Remember, lambda i's are positive and Vi's form an orthonormal basis. Given this, I want to show that M has a square root. First thing would be to break up lambda. So define Yi to be the vector square root of lambda I Vi. Notice that I can take the square root because lambda is a positive. If I write it like this, then it is easy to note that M is summation Yi Vi. We know that M is summation Yi Yi, where I have defined Yi. I again want to decompose it into two parts. We noticed that this worked because Yi was square root of lambda I Vi. Notice that even if lambda i's were negative, because I am working in complex numbers, I could have defined square root lambda I. These things would have turned out to be complex numbers. So what is the problem? I will let you convince yourself that if lambda i's were negative, then this equation will not turn out to be true. So if lambda is a negative, 1 will not be true. You need to convince yourself of that. That's the reason why we need lambda i's to be positive. Once we have this form, it is easy to construct B or the square root of M. We will put Yi's as the columns of this matrix. If B looks like this, you can convince yourself that B star B is equal to M. This shows that if M is PSD, then there exists a square root. There exists a matrix B such that B star B is equal to M. So we have shown that all three characterizations of PSD matrices are the same. One was that all the eigenvalues are real. Notice that this requires matrix to be Hermitian. So matrix is Hermitian and all eigenvalues are positive. This was the zeroth condition. One was that quadratic form was positive. This was VMV condition for all vectors. And then second thing was the existence of square root. These three conditions turn out to be equal. I would like to make a note here about this square root. The way we constructed B, it was of very specific form. It turned out to have orthogonal columns. Remember, Yi's are orthogonal because they are scalar multiples of orthonormal basis, and also it was square. In general, that is not necessary. as soon as you see that M is equal to some C star C, it means M is PSD. C could have non-orthogonal columns. It could even be a rectangular matrix. It doesn't matter. What we need is just this condition, and M turns out to be positive. If you have some confusion, that will go away when you notice that the square root need not be unique. In general, there can be many matrices such that M is equal to M1 star, M1, M2 star, M2, and so on. Though one particular square root is very nice, the one which we constructed in the proof. What I would want you to show is that the matrix constructed in the proof, or let me just say that if M is summation lambda I vi, look at this matrix, which is square root lambda I vi. This agrees with our understanding of even operator functions. In this case, this is going to be in itself a positive semi-definite matrix such that square root M star square root M is going to be M. This you can again very easily verify. And this turns out to be unique. So for any PSD M, there is a unique positive semi-definite square root. And generally when I talk about square root of M, I mean this unique PSD square. That is what we will remember when we will talk about the square root of a positive semi-definite matrix. The square root itself has to be positive. As an analogy, remember, if a number is positive, it can have multiple square roots, but generally we take the positive square root to be the square root. That is what we are going to do here. Thank you.